Okay, so as we've seen, research questions come in all shapes and sizes and types, and so of course there's a wide variety of research methods that you might use to try to answer different kinds of questions. But some properties of research designs are going to hold for any kind of research method whatsoever. And so Perry talks about several of these in the chapter. I'm going to focus here on reliability and then several kinds of validity, which Perry discusses in the chapter. So, what does reliability mean? Well, it's basically the idea that if somebody else did the research over again or used, a slightly different set of subjects or a slightly different procedure or something, that you would still be able to get the same kinds of results. So it doesn't matter who gathers the data, basically. And this is going to be maybe the single most important aspect of any empirical work. If somebody else did the research the same way, would they get the same results? And that particular notion, or the idea of trying to recreate somebody's research and see if it gets the same results, that's referred to as replication. And it's really considered essential to science, right? To any kind of empirical field. It shouldn't matter who's doing the measuring and who's doing the experiment. We want our procedures to be reliable, to return reliable results, because otherwise it's impossible to tell which effects are real and which ones are just an accident and whatever. Right? So at the extreme end, reliability means that ideally a machine should be able to collect your data for you, like a computer algorithm, because you design the data collection protocol so explicitly that there's no room for personal judgment or for systematic error or for any kind of bias, where bias here refers to not the social idea of being biased against people, but mathematical bias, where you have systematic things that shift your results in one direction or the other. Right? So the idea here is that if you don't design your procedures, whether they're experimental or otherwise, in a reliable way, then any effects that you get out of those data are just as likely to be due to one of these other factors, that is judgment, error, bias, etc., as they are to the question under investigation. So we find results, but if we're not using a reliable protocol for analyzing and gathering our data, then we don't know whether those results actually reflect reality or whether they're just sort of problems with the way that we gathered the data. So reliability is super important. And this includes sort of obvious things like doing fraudulent science, which are very, very, very rare. But it also involves a number of other kind of subtle things that you might not even think about. One of these is known in psychology as the clever Hans effect, and this is named after a kind of road show from the 19th century or maybe early 20th century, where this like carnival guy brought his brilliant horse Hans around to fairs and carnivals and things like that, and the horse, clever Hans, could solve math problems and answer questions about like geography and things like that. And it was this amazing thing where they'd write answers on the ground and the horse would walk over to the right answer, right? You'd ask the horse, hey, what's 10 plus 5? And he'd walk over to the answer that said 15. And it was like, oh my God, this amazing clever Hans horse. And it turns out what was going on here is that the trainer was able to give the horse subtle cues when it was standing near the right answer as opposed to one of the wrong answers. And the horse learned to read those physical or body language kind of cues from the trainer to know when it was doing the right thing or the wrong thing. So it's not that the horse actually could do math, but it was getting subtle cues from the trainer about when it was doing the right thing and the wrong thing. This can also happen during experiments or questionnaires or surveys or any kind of procedure that you're doing with subjects in it, with human subjects. You can influence their behavior in subtle ways that maybe neither you nor they even realize, but your conduct during the experiment can influence your participants. And more generally, this idea that the way you engage with human subjects can affect the way they respond to research stimuli. This is called the observer expectancy effect. It's the idea that if you're strongly expecting to get one kind of results, just all else being equal, you're way more likely to get those results. There's a certain kind of way for any kind of experimenter bias to creep into the entire research process, starting with interacting with subjects in this clever Hans effect, but it can also affect data analysis. Maybe I'm only going to do these analyses and I'm going to keep doing them till I find the effect that I want, and then I'm going to stop. It can affect the interpretation of data, right? So you have these particular quantitative results from our data, or maybe qualitative results from our data, and I'm going to interpret those so that they support the thing that I already believed before I started the research, even though maybe there was some other way to interpret those results at all. So for experimental effects where you're coding things, the best safeguard is to have a blind third party code the data if you're using any kind of a judgment or observer kind of technique. But failing that, it's also good to have strong protocols in effect in advance. So we're planning out exactly how we're going to do our research. We're not leaving ourselves wiggle room, right, to try to get the results that we want instead of the results that are actually in the data. So planning in advance is super important. In fact, this has become even more important, particularly in the psychological sciences in the last decade or so. They've been having terrible problems with these observer expectancy effects and with replicability. And one proposed solution is for everybody to pre-register their entire research protocol so that you go on record before the research is even done of saying exactly what you're going to do so that you don't leave yourself room to create observer expectancy effects. Within that world, these kinds of effects where you can analyze the data in a million different ways and sort of finesse the interpretation, this has become known as false positive psychology, or as the garden of forking paths, which I think is a really nice evocative name for this idea that you have a million ways you can shape the outcomes of your research, and you don't want to let your experimenter biases come into play in interpreting research. So that's all about reliability. Beyond reliability, there's several different kinds of validity that we want our research to have. What is validity about? Well, it's the basic idea that the things you're studying in your experiment or in your empirical work, whether it's qualitative or quantitative, that they bear some kind of veridical relationship to actual things out in the world that are important. Right? So the thing that you're studying in your experiment should be related to the construct that you're trying to draw conclusions about. And there's several different kinds of validity that get discussed, more so maybe in the experimental literature, although this is equally important in qualitative research as well. We're going to focus here on ecological validity. And what does that mean? Well, I've paraphrased it here as, to what extent are the conditions of your study like those that normally obtain in the real world? Right? So how much does your study actually look like the situations of interest that we're trying to learn something about outside the laboratory or outside whatever study you're doing, the classroom, whatever, right? So this real world idea, one important thing about the real world is that it is entirely uncontrolled, at least by us, right? We don't get to control the parameters of what happens out there in the world. And oftentimes when we're doing research, we're trying to figure out causal relationships, right? So what causes this thing? What causes that thing? Is this thing causally related to this other thing? So how are we going to do that in the real world where everything is uncontrolled? Where uncontrolled here is intended in the specific technical sense of an experiment where you're comparing two things, and the comparison is a controlled one if everything is exactly the same in the two conditions except for one parameter that you're trying to study. That's a perfectly controlled experiment. If there's a bunch of other stuff that differs between the two situations or the two conditions in a research study, then it's less controlled. It's uncontrolled to the extent that you don't have control over all of the parameters. Right? And of course, in the real world, we don't have control over an infinite number of parameters. Right? So the vast majority of the time, just by looking at what happens out there in the real world, we can't figure out causation. It's not possible, even in principle, to figure out causation by simply observing things that happen out in the world. And the same is going to be true of any kind of a study that uses real-world data in this way. These are sometimes called observational studies. And they can be useful for sparking research ideas or teaching us maybe some interesting things that tend to co-occur out in the world, but you can't use observational studies to learn anything about causation, right? And that's because the real world is not controlled. That said, it is maximally ecologically valid, and what that means is that we're always going to have a trade-off between being able to control the parameters that we're studying, which is super important if we're trying to figure out causal relationships, versus ecological validity. How lifelike is the research setup that you've used? And that's also important because we want to make sure that the things that we find are things that are actually relevant to the real world. But these two constructs, these two things that we want, right, tight control and ecological validity, they're always going to be in tension with one another to some extent. In general, it's exceedingly rare to figure out anything interesting by just observing undifferentiated natural processes, right? And so these are some sort of classic examples from the history of like hard sciences, but the exact same thing is going to be true for human sciences, social and behavioral sciences, right? We don't have Galileo's theory of gravity informed by watching raindrops fall, right? That's a perfectly natural process that certainly involves gravity, but you can't learn anything by going outside and trying to measure raindrops. Instead, Galileo performed some tightly controlled experiments to try to see how gravity affects different kinds of objects, right? Rather than using stuff that was going on around him in the world, he was dropping things from towers. He was thinking about vacuums and things like that, conditions that don't obtain out in the real world. Newton's first law of the motion of tree leaves, right? So Newton's laws of motion govern all physical objects in the universe to an extraordinarily precise margin of error. But he didn't figure that out by looking at tree leaves waving back and forth in the wind, right? Those processes are governed by Newton's laws of motion, but that's not a way to study something. Instead, you need to make idealizations and simplifications and try to study one parameter at a time. Watson and Crick discovered the structure of DNA, but they didn't do that by taking x-rays of people walking past on the street. That's not a way that you can learn anything about the molecular structure of deoxyribonucleic acid, or I'm sure I just messed that up, whatever the actual DNA stands for. Instead, you need to carefully isolate particular tissues in a laboratory in a setting that doesn't look anything like the real world in which DNA works in order to figure out the structure of that substance, right? You don't learn about basic entities of reality by just randomly observing stuff that's going on around you. That's not how science works. And what I'm trying to point out here is that the same is going to be true of sciences that study human beings. So we do need tight controls in order to actually learn about the relationships between different constructs and different phenomena out there in the world. But that said, controlling a study will limit our ability to generalize, and that's exactly why we think ecological validity is also important. We want to be able to generalize our results to other situations that are not the specific situation we've created in the lab, right? This is part of what research is. It's seeking generalizable knowledge. So if we only study, for instance, people reading a script in a laboratory, then we don't know whether whatever results we find are going to also apply to people speaking in their home, or whether it's just an artifact of the fact that they're reading a script in a laboratory. And presumably the answer to that question is going to depend on exactly what we're studying. So maybe some things do generalize from the laboratory to a casual conversation in your house, and maybe some other things don't, right? And it's hard to know. And the same is going to be true more generally. If we control some parameter P in our study, then we don't know whether the results of our study are going to generalize to other values of P, right? By definition, we're looking at a very limited range of possibilities when we do, or of possible scenarios when we do a controlled experiment. That's what control means. But that also can inherently be in tension with the ability to generalize because we've only studied a small range of controlled situations. So this is the trade-off, right? We have to sort of reach some kind of a satisfactory answer that's going to trade off these two factors against one another. What does that mean? Well, there's no right answers. There's always going to be a trade-off between how controlled a study is and its ecological validity. And this is an ongoing tension in, probably every academic field, but certainly in the language sciences. This is always a tension. People argue about this. You get lots of back and forth, and solutions to this trade-off are going to fall on a continuum, just like any trade-off. So you can have extreme end number one, only use observations that occur naturally in the world without any intervention from the researcher. So that would be something like insisting that you can only use corpora of natural speech to learn things about language or something like that. And then we can rely on natural variance to try to separate variables that are confounded, that aren't controlled. And that might work, but only if we have lots and lots of observations and if we have the right variables to begin with, right? So that's the idea, is that, well, we haven't tightly controlled for this particular factor, but maybe because the factor varies in natural situations, we'll be able to figure out, disentangle the effect of that factor and this other factor on the thing that we're studying. The other extreme endpoint would be only use rigorously controlled laboratory procedures that can be precisely replicated and that manipulate only one factor at a time. The null hypothesis here would be that effects don't vary between contexts. And that null hypothesis, and a null hypothesis is a kind of default, we'll talk about that in detail in a minute, is that, well, if we find an effect here, then it's the same effect we're going to find everywhere else. Of course, if we want to study that more explicitly, then we can do that with the next experiment. We'll expand it to another set of contexts, and in this way, we can build up our knowledge. Right? So these are, pretty close to actual real positions that some people take in linguistics. There are people who think you should really only be using corpora of natural speech, and there are people who really don't trust anything unless it's confirmed with a rigorous laboratory experiment. And then every position in between these two extremes is also a potentially valid position, because it all depends on how much you value these different desirable properties, controlledness versus ecological validity. And there's no real right answer there. So my personal take, and this is informed by my own research, I tend to be a little bit more on the control side. I think it tends to be more important than ecological validity in a lot of the situations that especially language scientists find ourselves in, right? Of course, both factors are important. I'm not denying that ecological validity is a worthwhile thing to want, but there's a problem with this confounding. And confounding means that when you're looking at two different situations and trying to learn something about the difference between them, the number of things that differs between those two situations is not just one, but it might be 10 or 100 or an infinite number of differences. And we say all of those factors, the contrast between the situations, are confounded with one another. And this is a property of natural observations out there in the world. In the world, everything is confounded pretty much, right? So it's very hard to separate out single factors by observing natural variation. And the problem is that once your data set is confounded, it's confounded forever. You can't undo that. But if you study a very narrow range of situations, it might hurt the generalizability of your findings, but you can always study generalizability incrementally. If you're worried about whether this effect is also going to extend to this new situation, then you can do another experiment with the new situation and find out. Right? Whereas once you've mixed up all of your factors, they can't ever be unmixed. It's like stirring food coloring into a glass of milk or something. Once you get that food coloring in there, the milk's purple forever. You can't get the purple out. Now, this is, again, my personal view, and it's not the only valid view. This is where I tend to fall, and not coincidentally, a lot of the things that I study, which mostly have to do with phonetics, they seem to vary to some extent quantitatively, but not really qualitatively between differently ecologically valid contexts, right? So the kinds of things I study, the size of the effect might be a little bit different in casual speech than it is in laboratory speech, than it is in, I don't know, more formal speech registers versus natural conversation or whatever. But it's not like the entire effect is going to change direction or disappear in different contexts. Our kinds of acoustic phonetic reflexes of talking tend to be quite robust across different contexts and vary only in their size, not in what they're actually doing. So, of course, to me, I'm less concerned maybe about generalizability and ecological validity than I am about tightly controlling a data set, which is super, super important in phonetics. Of course, other people can come to different conclusions about this. So I wanted to go through a few case studies here. I'm going to split this off into a separate video and just invite you to think about some of these setups and think about the ways in which they fall on this continuum and how they trade off these properties. I'll do that in a separate video.